we're looking at 1-4, inductive reasoning. All right, so inductive reasoning is a type of reasoning that reaches conclusions based on patterns of specific examples or past events. All right, so our first example, can we use inductive reasoning to determine what appears to be the next term in the sequence? Or how can we use that? All right, so if I'm looking at this sequence here, 88, 82, 76, 70, 64, I can see a pattern where we are subtracting 6 from each previous term. So if I continue, my next term, so 64 minus 6, I'm going to get 58. And then 58 minus 6, I would get 52. So those are going to be my next two terms in this sequence. All right, the next one's not quite so easy. 3, 5, 9, 15, 23. Okay, to get from 3 to 5, I would have to add 2. But adding 2 to 5 would get me 7, not 9. So 5 to 9, I would have to add 4. 9 to 15, I would have to add 6. Okay, so I'm going up by 2 every time I add. I would add 8. So next to my 23, I would need to add 10, which would get me 33. To that 33, I would then add 12, which would get me 45. Okay, so far we've seen an example where we are subtracting, one where we are adding and increasing each time. This next one's a little bit different, and I added in here to give us an extra example before we start trying it on our own. Okay, so now we have 18, 54, 162, 486, and 1,458. Okay, so on this one, if I take 18 and I multiply it by 3, that's going to get me my 54. Write this as a... Okay. Now if I take 54, multiply that by 3, that gets me 162. Multiply 162 by 3, that gets me the 486. Multiply the 46 by 3, that gets me 1,458. Multiply that by 3, that's going to get me 4,374. Now I want to multiply that by 3. That's going to get me 13,122. Okay. So now our try-it problems. Okay, so what is the next, what appears to be the next two terms in each sequence? So we've got 800, 400, 200, 100. Well, I can tell that this is being halved each time, so I would divide by 2 for each sequence here. So half of 100, I would get 50 for my next term. And then half of 50, I'd get 25 for that next one. All right, next I have 18, 24, 32, and then 128 over 3. Okay, so this one's a little bit trickier. We can see that our number is increasing, but it's not doubling. It's not quite doubling. So it's going to be increasing by a number less than 2. So to find what it's increasing by, the easiest way to do that is we can take 24 and divide that by 18. And that's going to give us what it's increasing by. Okay, once I simplify that, I would get 4/3. Okay, so my pattern is that we are increasing by 4/3 each time. So it'd be multiplying by 4/3. Okay, so when I take the 128/3, multiply that by 4/3, I'm going to get 512/9. When I take that, multiply it by 4/3, I would get 2048/27. Okay, next we want to use inductive reasoning to make a conjecture. And a conjecture is an unproven statement or rule that is based on an inductive reasoning. Okay, so our example, what conjecture can be made about the number of dots in the nth term of this geometric pattern? All right, so term 1, there are 2 dots. Term 2, there are 6 dots. Term 3, there are 12 dots. Term 4, there are 20 dots. So what can we conclude, what conjecture can we make about what is happening each time? Okay, so let's kind of sketch this out. So if I take that last one, got 5 across. Gosh, get my pen. 1, 2, 3, 4, 5, and then 4 up. All right, so depending on how many rows, that is our n value. There are n rows. And then for each row, we add 1 to get the number of columns. So n plus 1 gets us our columns. All right, and our terms are n. Okay, so the conjecture that we can make is that our nth term will contain n times n plus 1. Because to find area, we multiply length times width. So our length times our width is the n times n plus 1. Okay, we could also simplify this to n squared plus n if I distribute that n at the beginning. And we are finding the number of dots when we use that. Okay, so that would be our conjecture. All right, our try it. A, how many dots are in the 5th and 6th terms of the pattern? Okay, so this one has a little bit different of a pattern. Okay, and to find this one, I can see that I'm finding a square in each of these, and then on top I have 1 less than that square. Okay, so to put that into variables, if my term is n and my term here is 4, then I would have n as this term, and then n for that side. that gets me the square, but I need to now find those top 3. So I would then take for these top 3 n minus 1. Again, to find area, we take length times width, so n times n. Well, n times n is just n squared. So I would have n squared to find me the area of that square, but now I need to add to that those top 3 or 2 or however many is on top. So n minus 1. Okay, so now if I'm finding the 5th term, I'm just going to plug in 5 for n. So 5 squared plus 5 minus 1. It's going to give me 29 for my 5th term. Then for my 6th term, I'll plug in 6. It's going to get me 41. Okay. What conjecture can you make about the number of dots in the nth term of this pattern? Okay, well, we've already come up with that conjecture. We wrote it up above. So our conjecture is that the nth term will contain n squared plus n minus 1 number of dots. Okay. Right now we're making predictions. So we have some data in this table about residents who have voted in the 7th town council election. Okay, and to find our pattern to make predictions here, I'm going to zoom in so we've got some more room. I'm going to take the number of voters and divide that by the total residents to figure out what percentage of the residents actually voted. So 386 divided by... Okay, and I'm going to keep doing this all the way through this data. So I have all of that data to figure out what percentage of residents actually voted. Okay, so when I'm looking at this, if I'm finding the average, I'm going to find that roughly about 11% of residents actually voted. So if my total residents were 7,786 for that 7th year, and only about 11% of those, so 0.11 actually voted, then that means that 856.46 voted. Well, we can't have a portion of a person who actually voted, so we're going to round that down. right, or try it based on the data. How many members would you expect the chess club to have in the 5th year? Okay, so between our 1st year and our 2nd year, we added 3 people. 2nd year to 3rd year, we added 4. Looking at the wrong one. And then 3rd year to 4th year, we added 5. So for our 5th year, I would estimate that we are going to add 6 people if we continue that pattern of adding 1 each year. So if we increased by 6 from the 22 members, we would end up with 28 members in the 5th year. All right, next, we want to find counterexamples to show a conjecture is false. So we're trying to find some information that will prove that our conjecture is false. Okay, so our conjecture is that a polygon with diagonals has 2 fewer diagonals as sides. All right, so let's start thinking of some different polygons. So if I have a 4-sided, that would give me 2 diagonals. Let's move on to 5-sided. That's 6-sided. Hold on, let me try that again. There we go, 5-sided. Okay, so 5-sided, if I draw my diagonals, let me try this again. My diagonals are not showing up very good here. Try a different tool. Try some. So my diagonals. Okay, so I can see that I have 5 sides. And there are 1, 2, 3, 4, 5 diagonals. Okay, well, I can already see that I'm proving this conjecture wrong because a 5-sided object has 5 diagonals and not 3 diagonals like our conjecture is trying to prove. But let's go ahead and do one more. Let's do 6-sided. Okay, and then we'll do our diagonals. Okay, I think I have all of them then. So I've got 6 sides, and I should have 9 diagonals. Okay, so we have proved this conjecture wrong. And we can prove it false by just finding one counterexample that is false. What is a counterexample that shows the statement, the sum of two composite numbers must be a composite number, to be false? Okay, and just a refresher, a composite number is a positive integer that is formed by multiplying two smaller positive integers together. So in order to get a composite number, we have to multiply two numbers together to get it. So if I can add together two numbers that would give me a prime number, then I would be able to prove that this does not work, because I cannot get a prime number by multiplying anything else together. So if I took 3 and 16 to get me 19, that's going to prove this conjecture false. Another example, if I added 5 and 8, that'd get me 13. If I added 1 and 2, that'd get me 3. Okay, so if I can add two composite numbers together, that would get me a prime number. My counterexample is proven false. Okay, so if I add two composite numbers that add to a prime number, then my counterexample is false. All right, next we're going to test a conjecture. All right, for the conjecture, we want to test the conjecture with several more examples, or find a counterexample that disproves the conjecture. All right, so our first one, a polygon with 4 congruent sides is a square. Okay, to have a square, each corner ends in a 90-degree angle, and each side is congruent to each other. Okay, so they're telling us that a polygon with 4 congruent sides, so if it has 4 congruent sides, so they're assuming that we are going to draw our polygon this way, which would prove that conjecture true. But if I can draw this a different way, where it is not a square, then it would be false. So if I slanted this and created my angles that are not 90-degree angles, but all of my sides were still congruent, then I would be proving it false. Okay, so if I had a rhombus, has 4 congruent sides, but does not form a square. Okay, so this conjecture is false. All right, next B, if a number is a multiple of 9, then the sum of its digits is a multiple of 9. Okay, so let's try a couple. So 9 times 3, I'd get 27. Well, if I add 2 and 7 together, I get 9. Well, that is a multiple of 9. About 9 times 12, I'd get 108. 1 plus 0 plus 8, I would get 9. Well, that's a multiple of 9. 9 times 27, 243, 2 plus 4 plus 3, 6, 7, 8, 9. So that's 9 again. Let's try a little bit bigger, 154, 6. So 1 plus 3 plus 8 plus 6. Well, I'm going to get more than 9 this time for sure. But I get 18, which is a multiple of 9. So this conjecture is true for the cases that we tested. We only tested 4, but so far every single time we tested it, it does appear to be true. Let's look at our try it. All right, we want to see if we can disprove these. All right, for every integer n, the value n squared is positive. Okay, well, what if n is 0? 0 squared is just 0. 0 is neither positive or negative, so this would be proved false. All right, B, a number is divided by 4 if the last 2 digits are divisible by 4. All right, so I'm going to take a number and divide it by 4. And we want to make sure that our last 2 numbers are divisible by 4. Okay, so I took that divided by 4, I get 78. It is evenly divisible by 4. I get a whole number when I divide it by 4. And then if I take my last 2 numbers, so 12, divide that by 4, it is evenly divisible. Try another. Divide that by 4. I would get a whole number. So it appears to be divisible by 4. Well, let's see if I can do this a little bit quicker, and I'm taking the last 2 numbers and dividing that by 4. Well, that gets me 6, and that is a whole number. So it appears to be working so far. Let's try again. Okay, I get a whole number when I divide by 4. So now we're going to try our shortcut of 36 divided by 4. And I get 9. Okay, so far for the year that we have tested, this does appear to be true.